everyone, this is me, Miss Leia, and in this video, we're still going to talk about freely falling bodies, but this time, we'll focus on the learning target on executing the problem-solving steps for a drop freely falling body. So if you can still remember, there are three cases for free fall, case 1, case 2, and 3. And for this video, we're only going to talk about case 1, which is drop objects, okay? Now, there are a few things that you have to remember for case 1 of free fall. And the first thing is the magnitude of the initial velocity for a dropped object is 0 because you're not imparting any momentum on it. And the sign of the initial velocity, of course, is none because there's no such thing as negative 0 or positive 0. Okay. Going forward, I like us to watch this video clip from The Big Bang Theory. It's a really fun sitcom, and there's a certain scene there that I'd like us to focus on where we can actually derive a certain free fall problem, which is also interesting. Now, in that video, it says that Lois Lane fell from the helicopter, and when Superman caught her, she was approximately moving at 120 miles per hour. I converted it to meters per second for convenience, and it's 53.64 meters per second. Now, the question that I constructed for this particular Big Bang Theory scene is how much time in seconds elapsed before Superman was able to catch her. Okay, and from there we're gonna go as nerdy as Sheldon because we're gonna figure out something numerical out of this Superman scene. Okay, so the first thing that we have to do is just the usual problem solving steps. We're gonna list down all the given variables in the problem as well as the RTF or required to find and the missing variable or MV. So let's start analyzing this. Okay, starting from the moment Lois Lane fell from the helicopter, how much time elapsed before Superman was able to catch her? Okay, now we can assume that this is case one project free falling body because the initial velocity is obviously zero. So the problem doesn't tell us that Lois Lane was propelled downward by someone or something. So we can say that she just fell out of the helicopter, and therefore we can assume that initial velocity is in fact 0 meters per second. Okay, and then her downward speed when Superman caught her was approximately 53.64 meters per second. Okay, the reason why I converted it to meters per second is because we were using SI units, okay, not miles per hour. Okay, so let's record it down. Obviously, that's the final velocity, and that's 53.64 meters per second. So I hope that you can imagine the scenario. So if this was Lois Lane, for example, she's falling downward, and this is where Superman is. Okay, and then there's a cave. It looks like a bat or something. Mo. Oh, anyway, so the initial velocity is 0 meters per second, but at a certain point, right before when Superman caught her, that was moving already at 53.64 meters per second. Therefore, that is what we will consider as the final velocity. But there's more, and you have to be very careful with this one. You have to add a negative sign. So it has to be negative 53.64 meters per second. Why? It's simply because Lois Lane's velocity is actually directed downward. So if the motion is downward, that velocity should be given a negative sign. I hope that's clear. Now, there's one more given that's automatic when you're talking about freely falling bodies, and that is acceleration, which is negative 9.8 meters per second squared for freely falling bodies here on Earth. Okay? This isn't always negative 9.8 meters per second squared. Yes, whatever case of free fall, whether it's case 1, case 2, or case 3, it's always negative because the force that causes this acceleration is directed downward. Its gravitational pull is always downward. So the acceleration it does is projected downward as well. So always give it a negative sign. So it's always 9.8 also as long as we're talking about Earth. Of course, in other planets, it has a different value, but it will be stated in case. Okay, now let's continue. What else do we know about the problem? No more. There are no other given. Okay, so let's go back to the variables that we know. We have v sub I, or we have VV, that right? So these are the variables that we deal with in kinematics or in UAM in particular. And v sub I, v sub F, and acceleration, they are all known. They are all given in the problem. And also, it says how much time elapsed before Superman was able to catch her. So the RTF in the problem is actually time. Therefore, the missing variable is the displacement. Why? The missing variable is the variable whose value is not known in the problem, but it's also not the required to find. So the missing variable would be displacement. So what if the missing variable is displacement? Once again, we pick the equation based on the missing variable. Okay, so let's say for example, the missing variable is displacement. We're supposed to choose equation 1, right? Because it doesn't have displacement in it. Okay, so the final working equation will be Vf equals v sub I plus acceleration times time. Okay, that's our final equation. Now wait, I'd like you to notice something among the given. You can actually see that initial velocity is 0. And in that case, you can cancel it from the equation because it's 0, right? So this will reduce down to v sub f equals acceleration times time. Okay? Now, we have to modify it further because the RTF, as you can see, is actually time. So if time is the RTF or required to find, we have to isolate that. Now let's do this in the next frame. Okay, so far, v sub f is equal to acceleration times time. So if you want to isolate time, it's simple. We just divide both sides by a. So just remember that if there's a multiplication operation between the two variables, so acceleration times time, for example, you will divide it by the variable you want to get rid of. That's the procedure. Do not transpose it. You're not allowed to do that. You have to divide it, okay? You can transpose this on the other side if there's a plus or minus sign. So that's what you have to remember. In this case, where there's a multiplication operation, acceleration times time, the way you can cancel it would be through division. Okay, so we're gonna have cancel it. Okay, it's time equals v sub f divided by a. Okay, now all we need to do is to plug in the given. So you have to go back and we can see that v sub f is 53.64 meters per second with a negative sign, and of course acceleration is negative 9.8 meters per second squared. So this is 53 meters per second. Wait, sorry. We're just plugging in the variables now. So 53.64 meters per second divided by negative 9.8 meters per second squared. Okay. Now let's do the math. We're going to use a calculator. I think in college entrance test, they're going to use 10 for the gravitational acceleration value for simplicity since you're not allowed to use calculator. But this time, let's use a calculator to be more precise with the values. Okay, so using your calculator, you're supposed to get 5.47 seconds. Cancel, 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 cancel with the remaining S. Okay, so the final answer would be time equals 5.47 seconds. There you go. So you can actually notice that it is a pretty fast time. That's roughly 5.5 seconds. And yeah, it's really fast considering that Lois Lane has actually fallen from quite some time and that Superman had to catch up with where she was at that point. But of course, as what we have heard before, Superman is actually faster than a speeding bullet, so it's not quite surprising. Although Sheldon was not overreacting when he said that that particular scene was rife with scientific inaccuracy, which is actually normal for a superhero movie. It can really be that unrealistic. That's why adult supervision is really important when children of very young age watch this kind of movies to avoid developing any misconception on the children's part.